Thanks for coming, everybody. It's my great pleasure today to introduce Furtek for a very interesting talk on a formal design methodology approach to digital design. Fred's been working in this area for a long time, on and off with his work in startup companies and field programmable gate arrays and so forth. He tells me he started this formal verification stuff around 20 or so years ago at was it MITRE and Draper Labs and places like that. I've known Fred since the days when we worked together on some FPGA stuff at Apple Computer back in the early 90s. And there's a lot of good ideas here. So, Fred, take it away.
All right, thank you. Let me mention first that this talk is based on a paper that I've just submitted to IEEE's Computer Magazine. If anyone would like a preprint of that or a copy of it, it was just submitted. Dick Lyon has a copy, and please give him, send me an email if you'd like a copy. All right, this is technology I've been working on for quite a while. It's a formal approach to verifying the behavior of digital systems, and I want to emphasize it's for both hardware and software. I make no distinction between the two. How do I get this little guy to go away here? Nope, that didn't do it. All right. With rare exceptions, digital design, both hardware and software, is based on trial and error. We have incredible reasoning powers. Humans have created extraordinary complex systems, but our reasoning is not infallible. We make mistakes, and we rely on verification to detect those mistakes, find where we've made mistakes, and correct them. But the standard verification techniques, debugging, simulation, and emulation, can only prove the existence, not the absence of bugs. So when we feel we've got the system working, we think we've got it working right, we ship it or we deploy it, but we often find from our customers or sometimes from hackers that we haven't quite got it right. There's bugs, or there's vulnerabilities in our systems. And my thesis is that there can be no fundamental advance in the reliability and the security of our systems until we move beyond this process of trial and error. So what's the solution? I'm going to list 4 requirements for methodology to take us beyond trial and error. The first is we need a mathematically rigorous methodology. There simply is no substitute for mathematical rigor. Software engineering can do only so much, but at the end of the day, we need mathematical rigor. It also must be said that to have real impact, the methodology must be usable by the average engineer. If the technology is onerous to use or it's incomprehensible except to an elite group of highly skilled, highly educated experts, it's simply not going to have an impact in industry. Now, I'm not saying anything new here, except maybe requirement 2. There's been a recognition that we need mathematical rigor in verifying the behavior of digital systems. And this field, this area, has gone by the name of formal verification. And there has been work in this area for at least 30 years. And I want to very quickly cover 3 approaches. There are purely Boolean techniques. And within this area, there are 2 classes of tools. There's equivalence checkers and satisfiability solvers. These have been extraordinarily successful. They have very simple interfaces, and they can handle tens of thousands of Boolean variables. The problem with these purely Boolean techniques is they cannot handle time. And the approach I'm going to describe does handle time, and it does it in a unique way. But let me add that these purely Boolean techniques are the perfect complement to what I'm about to describe. There's another approach called Theorem Proving, and the center of research in that area is SRI up in Menlo Park. In this approach, formal logic is used to prove properties about the system, the technology is extraordinarily powerful, and they have extraordinarily expressive proof systems. I'm a great admirer of theorem proving. The problem with theorem proving is that it's not automated and it requires a good deal of skill on the part of the user. And if you've got a PhD in formal logic and a lot of time on your hands, this is the technology for you. But there is one exciting prospect is to integrate theorem proving techniques with the automated tools I'm going to describe in a moment. Now, the approach that's received the greatest amount of effort over the last 30 years is something called model checking. There must be at least 100 or a couple of hundred researchers around the world that have been working on model checking. It's an automated verification technique in which temporal logic specifications are checked by an exhaustive search of the state space of a concurrent system. The fundamental problem of model checking is it must address the state space explosion problem. And to give you an idea of how significant that problem is, a system with one flip-flop or binary variable has two states. A system with 10 flip-flops or binary variables has 1024 states. And a system with 100 flip-flops or binary variables has this ridiculously large number of states. Now, for the past 30 years, the efforts in model checking have been directed at mitigating the state space explosion problem. And they've developed some quite impressive heuristics. For example, they've gotten to the point where they can handle hundreds of binary variables, flip-flops. They can't handle, as far as I know, thousands or tens of thousands. And of course, there are systems with a great many more than a few hundred binary variables. However, as clever as they may be, at the end of the day, they're addressing only a symptom of a much deeper problem, and it is that underlying problem which must be addressed. And that problem was articulated extremely well by Edward Lee, who is chairman of electrical engineering and computer science at Berkeley. And I'm quoting, "The physical world is highly concurrent, and our very survival depends on our ability to reason about concurrent physical dynamics. The problem is that we have chosen concurrent abstractions that do not even vaguely resemble the concurrency of the physical world. We have become so used to these computational abstractions that we have lost track of the fact that they are not immutable." I think he's absolutely right on the money. And the problem with model checking is that they have chosen an abstraction, finite state machines, that does not even vaguely resemble the concurrency of the physical world. So what's the answer? Where do we look for an answer? Where do we get a clue on handling concurrency? How do we do concurrency right? Well, I can think of no better place to look for an answer than those non-digital disciplines like physics and electrical engineering that have the mathematical machinery to deal with concurrent physical dynamics in a wide range of systems. I mentioned those two disciplines in particular because as an undergraduate, I majored in electrical engineering. And all of the systems we studied, both in physics and electrical engineering, innumerable courses I took in those areas, everything we studied involved concurrent systems. And yet the terms concurrency and parallelism never arose. That's because concurrency was handled in a natural and a transparent way. So what's the secret to addressing concurrency? How do they do it? Well, distilling the approach into the simplest possible terms, each element of an analog system is modeled by a separate set of equations, and mathematical tools are used to derive or verify new equations describing aspects of the system's behavior not obvious from the initial equations. Now notice here that the model grows linearly with the size of the system. You add more components, more elements, you simply add the equations for those elements or components. There is no state space explosion. Well, how do we take this insight from the analog world and apply it to the digital world? Well, I've distilled what I've just described for analog systems. I've distilled that into the final two requirements. Each element of a digital system, whether it's hardware or software, must be modeled by a separate set of constructs. I'll get to exactly what those constructs are in a moment. And the same constructs must be used in modeling the system and also in describing the aspects of system behavior that you want to either derive or verify. So the question boils down to, what is the counterpart to the analog world's equation? What is it that we can substitute for equations in the analog world so that we meet requirements 3 and 4? The answer is implications. We're all familiar with implications in classical logic. If A, then B, where A and B are Boolean expressions. And it's commonly written A with an arrow followed by B. But classical logic has no notion of time. It cannot express, in particular, it cannot express implications distributed in time. And by that, and here are some examples of implications distributed in time. If A holds in a state, then B holds 5 states later. If A holds in a state, then B must hold within the next 5 states. If A holds in a state, then B holds therever after. If A in a state, then B until C holds, or simply B in every state, which is equivalent to if true in a state, then B in the same state. Now, these sorts of implications play a key role in how humans reason about digital behavior. I don't care whether we're talking about a programmer designing software or a hardware designer designing hardware. This is how humans reason about the behavior of the systems they're designing. Humans do not explore the state space because the human brain cannot possibly cope with the state space explosion problem. Now, is there a general form for implications distributed in time? And the answer is yes. It's based on integrating Boolean expressions and regular expressions. And I know that there's work going on here in code search using regular expressions. I assume I'll give you a very brief overview of regular expressions. First, let's start with Boolean expressions. They're constructed from equations and atomic Boolean variables using standard Boolean connectives, and or not, or whatever your other favorite Boolean connectives are. And equations are of the form Boolean variable equals a Boolean formula, or an arithmetic variable equals an arithmetic formula. Now, the important thing here is that we have arithmetic equations. And that's important because it's going to allow us to describe both the control and data path portions of a design. Regular expressions have been around since, I guess, the very early Unix days with the inclusion of the grep utility. Regular expressions represent sets of strings. In our case, there's going to be sets of sequences of Boolean expressions. Regular expressions are very widely supported. They're supported by Google and Microsoft. There's 2 IEEE standards. I do want to mention one particular standard, and that's the IEEE P1850 property specification language, which is derived from a language called Sugar, which was developed by IBM. They also have incorporated within their language regular expressions over Boolean expressions. In fact, what I'm about to describe is a subset of this IEEE standard, although we've simplified the syntax. Now, traditionally, regular expressions are used to represent strings of characters, but we're going to use them to represent sequences of Boolean expressions. Now, we're going to enclose each Boolean expression within square brackets, and that will define a condition applying to a single state or clock cycle. Now, you will also see, and these will form the characters of the symbols of our Boolean expressions. So we're going to have, regular expressions. So we're going to have Boolean expressions enclosed in square brackets, and we're going to build up regular expressions using these. Now, you'll also see empty square brackets. That denotes the Boolean expression true, which is in effect represents a don't care state. since true holds in every state. So whenever you see empty brackets like that, like this, that's going to represent a don't care state or a don't care clock cycle. Now, our implications are going to be of two forms. We're going to have a regular expression implying a Boolean expression in square brackets. What that means is the pattern of behavior described by this regular expression implies that this Boolean expression holds in the next state following the sequence of states described by that regular expression. In this case, we're going to have a regular expression, and enclosed in the square brackets, we're going to have a Boolean expression implying another Boolean expression. What this means is the pattern of behavior described by this regular expression and also including this Boolean expression within that square bracket implies this second Boolean expression. Now I'll give you examples of that. Here are the examples I listed a few slides earlier of the implications distributed in time. If we want to say that B holds in every clock cycle or every state, we simply enclose B in square brackets. If we want to say that if A, then B 5 clock cycles later, we have a state in which A holds, followed by 4 consecutive don't care states, implying that B holds in the next state. So what this says is if A holds in a state, then 1, 2, 3, 4, 5 clock cycles later, B holds. If we want to say if A, then B within the next 5 states or clock cycles, we write if A is followed by not B, not B, not B, not B, then by God, in the next state, B ought to hold. If you want to say that if A, then B thereafter, we use the Claney star. The Claney star represents 0 or more iterations of a Boolean expression. So what this says is if we have A followed by 0 or more arbitrary states, then B holds in the next state. So what this says is if A holds, B holds 1 state later, 2 states later, 3 states later, and so on. And finally, in representing if A, then B until C, that's represented as A followed by not C an arbitrary number of times. In other words, if we haven't reached C, if C has not yet held, and in the final state, if we have C has not yet occurred, then B holds. So this is a very general formalism for representing implications distributed in time. I call those temporal implications. So now, rephrasing that sentence we had for analog systems, we can now rephrase that as each element of a digital system is modeled by a separate set of temporal implications, and mathematical tools are used to derive or verify new temporal implications, describing aspects of the system behavior not obvious from the initial temporal implications. But what are the mathematical tools referred to here? This is a technology I call Torics. It comes from combinatorics. And the reason I'm emphasizing combinatorics is because the underlying mathematics is a body of combinatorial mathematics. And you can see that mathematics in a paper that's published in the Journal of Combinatorial Theory quite a few years ago, actually before I joined Dick at Apple Computer. That's the fundamental theorem. There's also a much longer paper that was posted on the web at archive at arxiv.org last year that builds on the fundamental theorem. And there's a very substantial body of combinatorial mathematics in there. That mathematics supports 3 automated verification tools: an inference engine, a verifier, and a simulator. Now let me very briefly describe the Torics methodology. There are 5 steps. In step 1, a digital design, whether it's hardware or software, expressed in a standard programming or hardware description language, is converted into a set of temporal implications. Step 2. Now this is a little counterintuitive, so bear with me. Each temporal implication of the form regular expression implies Boolean expression is converted into the regular expression RE not BE. Now we've accomplished a couple of things here. We've gotten rid of the implication. And in so doing, and we've gotten rid of the implication and we've converted into something that's purely a regular expression. That greatly simplifies the underlying mathematics and the algorithms. Now how do we interpret this? This expression says that the pattern of behavior RE must be immediately followed by the Boolean expression BE, which means that if we have RE, we cannot have not BE. In other words, what this describes is a disallowed or forbidden or prohibited pattern of behavior. And we're going to do the same thing with the other form of regular of implications. We're going to convert an implication of this form into a regular expression of this form. This also represents a disallowed or prohibited or forbidden pattern of behavior. Now, this is necessary in order to get in order to apply the mathematical machinery and the algorithms based on that mathematics. Is this clear? Is there anything confusing about what we're doing here?
Because the algorithms don't handle implications.
The algorithms could be designed to, it's a lot simpler to do it this way. It makes the mathematics simpler. It makes the algorithm simpler. Now, from the standpoint of the user at the input and at the output is going to see implications. But the mathematical machinery internally is going to be working with these regular expressions representing disallowed patterns of behavior. Step 3. Now, those of you who have taken elementary automata theory know that we can convert a regular expression into an equivalent finite state automaton. And that's precisely what we do. But let me emphasize that this finite state machine, this finite state automaton, is nothing like the finite state machine used in model checking. There they have a combinatorial explosion. Here, this finite state machine grows linearly with the size of the system. The regular expression grows linearly with the size of your system, and the equivalent finite state machine also grows linearly with the size of your system. There is no state space explosion. Now, step 4, we take the automaton, the finite state machine created in step 3, and we supply that to either the Torics Inference Engine or the Torics Verifier. And either tool, both tools, return a new automaton, a new verified automaton, which represents the property you're either deriving or verifying. In the last step, we take that that resulting automaton, which was produced by the inference engine or the verifier, we convert that back into a regular expression, and then convert that regular expression back into a set of verified temporal implications. That, in a nutshell, is the methodology, the Torics methodology. Now, the inference engine, let me briefly discuss the 3 engines, the 3 tools. The inference engine is a fully automated tool that derives or infers new temporal implications from existing temporal implications. It can be used, and this is its most important, the most significant use of the inference engine, is to derive the input-output or the black box behavior of a digital design. The I/O behavior is obtained by resolving and deleting the hidden or internal signals. Now, resolution, for those of you who have some experience in formal logic, is an inference rule a very powerful inference rule in formal logic. And what we've done is we've adapted that resolution principle to handle sequences of Boolean expressions as opposed to just individual Boolean expressions. The description produced by the inference engine, the I/O behavior, mentions only the input-output signals. The initial input to the tool mentions both internal and input-output signals, but what the tool produces as output mentions only input-output signals. So using the jargon of the field, a behavioral model can be automatically extracted from a structural model, thereby supporting encapsulation and information hiding. Now, I'd like to give you an example. For those of you who have a background in signal processing, you will know that FIR stands for Finite Impulse Response Filter. And what I have here is a design created by a very talented engineer. He's just extraordinarily clever. And he came up with a design in which he has multiply accumulates. And the result is that the computation for two output variable values are distributed temporally over 4 clock cycles and spatially over 2 multiply accumulates. It's a rather intricate design. I've actually simplified it. He had 8 multiply accumulates, but I simplified it down to 2. So we have, in this example, there are 2 Boolean variables, reset, start a frame, and we have 13 numeric variables, and we have 4 numeric constants. This is a block diagram, a schematic of his design. And here we have, and it was very straightforward to take his design. There was no difficulty in translating his design into a set of temporal implications. And we've divided it into those implications describing the control and those describing the data path. Now, what I have here on the left are the actual temporal implications. And what I have on the right-hand side is the English language interpretation of each one of those. And so we have 5 control, and we have all of the remaining are data path implications. There's a total of 33 implications here, temporal implications. Now, we then supply these 33 temporal implications plus a list of the input-output signals. And the input-output signals are reset, X, and Y. So we supply the implications, and we supply a list of the input-output signals to the inference engine. And in about 1 second, the inference engine returns a single temporal implication. And it is of this form here. Now, first of all, let's look at, here's our implication here. Let's look at what's being implied. Here we have contained within these square brackets a single arithmetic equation. This says that y equals the constant h3 times this, so on and so on. This is, for those of you who have studied digital signal processing, you will recognize this as an 8-tap symmetric FIR filter. And now so it implements an 8-tap symmetric FIR filter. Now let's look at the premise, what's to the left of the implication. We see here, contained in square brackets, reset equals 1. In other words, reset is asserted in this state. And then we have 1, 2, 3, 4 following states, arbitrary states. And then we have a pair of states in parentheses with declining star, which means that we can have 0 or more iterations of this pair of states. So The first output is produced when this is 0, when there are 0 iterations of this. So when we assert reset, then 1, 2, 3, 4, 5 states later, we produce this output. So 5 states after we assert reset, we get an output. And this little couplet here with the Kleene star means that we're going to get a new output every other clock cycle after we assert reset. So we'll get an output 5 clock cycles, 7 clock cycles, 9 clock cycles, 11 clock cycles thereafter. So both the timing and the functionality of this system are contained in this single temporal implication. So we have timing and we have functionality. And so we've taken all of these implications, 33 of them. And by the way, you can look at these temporal implications and you can noodle on them as this designer did. When he designed the circuit, he did not have this tool. And he created a spreadsheet like a spreadsheet of all of these. He had a spreadsheet of various formulas, and he would stare at them and noodle on them for hour after hour after hour, convincing him that in fact this did implement what he wanted it to. In this tool, in about 1 second, we can produce this representation of the input-output behavior. And it's exceedingly non-trivial, by the way, deriving this implication. Now the verifier, yeah?
I was curious why you have all the don't care states as opposed to states that don't assert that another reset signal happens.
Are you?
So here you're asserting reset, and then some number of don't cares follow, and I'm wondering why there isn't a reset equals 0 on the
In other words,
states.
reset equals 0? You're raising an excellent question. And in fact, when I first did this, I did in fact insert those in there, but it became rather tedious to do that. I have a special way of indicating to the program that a signal is asserted only once at the beginning, and reset is one of those. But you're absolutely right. To be perfectly rigorous about all of this, I would have, you're exactly right, I would have reset equals 1 in this state, and then I'd have reset equals 0, reset equals 0. All of the other states would have. The reason I haven't done it, it just gets tedious. It clutters, it really clutters things up quite a bit. So what I've done is I've allowed the user can specify to the tool that a particular signal is an initialization signal, and it will occur only once in the leftmost state. That way, I don't have to clutter up my diagram with all of these resets equals 0s. But that is an excellent question, and it's something that annoyed me when I first started doing this, getting all of these resets equals 0. And I mean, it was tedious, and it was just really cluttering up the diagram. And I says, wait, there's got to be a better way. So I allow for the user to specify to the tool that a particular signal occurs once. And reset is that it's an initialization signal, and it will occur once at the very beginning, and it will not occur again. And that eliminates an awful lot of clutter. The verifier. The paper has an example of the clever little 2-bit counter and how the verifier works. I just decided to cut it from my slides. The verifier, unlike the Inference Engine takes just one set of implications describing a design and infers new temporal implications. The verifier takes 2 sets of temporal implications. It takes one set describing a design and another set of temporal implications describing a logical temporal property that we want to verify. And the verifier will then take the set of temporal implications and convert it into a regular expression and then convert it into a state machine. And it will then transform that state machine using this logical temporal property. And of course, and it will produce an output state machine which gets converted back to a regular expression which gets converted to a set of temporal implications. Now, what's unique about this verifier, in contrast to other verifiers, is in most cases it gives you yes or no. Yeah, it's verified. No, it's not verified. But what this can do is this verifier can indicate whether the property is satisfied in its entirety or whether a weaker version of the property is satisfied or whether no part of the property is satisfied. So that a user who is unsure of a system's exact behavior can make an overly broad conjecture, a conjecture the user knows is false, in order to find a weaker version of that conjecture that is true. And I don't have the diagram in front of me, but let me, in the paper, I have an example of a 2-bit counter. A 2-bit counter, a free-running 2-bit counter. And if you know anything about 2-bit counters, it produces a carry every 4 clock cycles. Well, the conjecture here, the conjecture was that it produced a carry every clock cycle. Well, that's not true. It doesn't produce a carry every clock cycle. But nevertheless, we know that's false, but we supplied that false conjecture to that 2-bit counter, and what it did was it transformed, actually I think I made a mistake. I said it transformed the state machine representing the design. It transforms the state machine representing the property. So what you get is a new property. So you supply it with the conjecture that an output is produced every clock cycle. That gets transformed into a new property which says that a carry is produced 3 clock cycles after reset and every 4th clock cycle thereafter. So we started out with a conjecture that was false, and we ended up with a verified property that was true. And we're getting very close to the end here. The simulator is, again, it's rather unique. I'm sure all of you, most of you have used simulators in your life. And there's something that's always bothered me about simulators, and that is that they're opaque. You have a massive input vectors, you get a massive output vectors, but there's nothing in there in that massive vectors that tells you what the cause and effect is. For example, if I have an anomalous output value, I'd like to know which input values cause that anomalous output value. Well, this simulator is based on the Inference Engine. First of all, you need the Inference Engine in order to use the simulator. What you do is you use the inference, if you know what the signals are you want to simulate, you use the Inference Engine to extract a set of temporal implications describing the behavior involving just those signals. And that set of temporal implications is used to drive the simulator. And now, if a user sees an anomalous output value, the user can query the simulator and say, why does this particular signal have this particular value at this particular time? And when the simulator receives such a query, it will identify the implication that it used to calculate that output value. It will also identify the input values appearing in the simulation that cause the implication's premise to be satisfied. It will also indicate the input values appearing in the simulation that are referenced in the implications consequence, the thing on the right-hand side. So we'll identify the input values that cause the premise to be satisfied, the premise being what's on the left side of your implication, and it will identify within the simulation the input values that are referenced by the consequence, what appears on the right-hand side of the implication. Conclusions. This technology provides a suite of mathematical tools to take us beyond trial and error design in digital systems. And I want to emphasize again, it's applicable to both hardware and software. I know the great emphasis here at Google is on software, but again, I want to emphasize that this is technology applicable to both hardware and software. The tools are fully automated. The input and output language. Well, on the input side, you can use, it's straightforward to design translators to translate a standard programming language or hardware description language into the language of temporal implications. But even temporal implications are not that hard to comprehend. I mean, if you know what Boolean expressions are, if you know what regular expressions are, it doesn't take much effort to understand the language of temporal implications. Concurrency is naturally expressed. We used as inspiration the approach of the analog disciplines like physics and electrical engineering. And I think if there's one key to the technology, it's the way in which we're expressing concurrency. And it's been said that we're entering the multi-core era. And I know Google is addressing that. And you bought Peakstream. I like to think of it as not the multi-core era, but the concurrency era, the area of concurrency. Google and every other company in the field is going to be facing serious issues related to concurrency. And they must be addressed. And because of our approach to concurrency, the model for a digital system grows linearly, not exponentially with the size of the system. What are the benefits of this technology? Well, increased designer productivity. For example, this engineer who noodled over his design for hours and hours and hours, trying to make sure, using his reasoning powers, trying to make sure that it did what he thought it did. Well, this could short-circuit a lot of that time and effort spent noodling over a design. It also reduces, it doesn't eliminate, but it reduces verification costs, and it improves time to market. And ultimately, it leads to systems, hardware and software that are more reliable and more secure. Thank you.
Any questions? Use the microphone. I have one. Fred, this notion that you got from Ed Lee about concurrency primitives that are closer to the way the real world works seems like a really good idea that maps well onto the small examples of hardware and designing filters and stuff like that. And I know Ed Lee is a digital signal processing guy too, like you and I are to some extent. And but when you get into the larger context of a computer system with software, you tend to have this thing in there called a RAM, where sort of any part of your system can screw up any other part by putting something in the RAM where it shouldn't. And there's this sort of infinite potential for long-range interaction between things that shouldn't interact. How do you capture that, model that, or make a design methodology where you can write implications that guarantee that you don't have that class of problem?
I have begun work on looking at modeling RAM. Let me just say that this is a work in progress. There's still a lot of work that has to be done on real-world examples. But you've got to start with a foundation that addresses things like concurrency in an appropriate way. And I don't claim I have all the answers. I haven't tackled huge problems. I've looked at reasonably small problems. But I think it's imperative that the industry, I don't know if it's Google, but the industry, somebody somewhere has to start tackling these problems. We have to get beyond trial and error. There has to be a mathematical foundation. I can't answer your question. I'm one researcher. There's only so much one person can do. I think that this is the foundation for the right way to do things. I think this is the foundation for the right way to address concurrency. And whether Google likes it or not, you're going to have to start addressing these issues. And peak-stream is, and what Intel and what AMD are doing are just the first timid steps in this area. But I do have to acknowledge my timing hasn't always been right. 20 years ago, I was working with Dick at Apple, and I thought all of this stuff was just right around the corner. You know that. Yeah. You know, I thought, you know, remember Larry Tesler, who was VP of Advanced Technology. You know, he was excited about this technology. By the way, this technology, actually, we kind of shifted into, it's all related. There's a common thread to the work I was doing at Apple in reconfigurable hardware and these tools, and that common thread is concurrency. In fact, it's common to everything I've been doing. But I thought the industry was about, you know, was right on the cusp of moving towards, and what do you want to call it, multi-core reconfigurable systems, whatever, back, in the late 80s, early 90s.
We're still on the cusp.
Yeah, we're still on the cusp. However, what had been happening for 50 years was we were just cranking up the clock cycle. Well, you can't crank up the clock anymore. And now the industry, everyone, the mainstream players, Intel, has to face up to the fact that concurrency is something that has to be addressed. And at least on the theory side, on the mathematical side, I've scanned the horizon. I've looked at what's available out there, and I don't believe that Theorem Proving, the folks up at SRI, what they're doing, they've been around for 30 years. In fact, I applied for a position there 30 years ago as head of that group. I didn't get it because my vision was very different from their vision. They want to do something very much akin to what mathematicians do when they prove theorems. It's wonderful stuff if you have that bent, if you like proving theorems, but it's not for the masses. It's not for the average engineer. And I look at model checking, and I think that any approach that involves exploring the state space is just, it's a dead end. It's just not the way to go. And maybe there's another approach out there somewhere that's occurred to no one. That's, you know, who knows? But of the approaches that I'm aware of, I think that this has the best handle on addressing issues of concurrency.
Another question?
On one of the slides, you mentioned that you could you take the design file and then the temporal implications file, and you can run some sort of formal verification to ensure that the design file is mathematically correct. Can the design file be, what format's the design file? Can it be more traditional type designs being verified against the temporal implications file, or does it have to be, is it a mathematically constrained design file, or?
The design initially can be a program written in C.
Okay.
Or Verilog, or that's a hardware description language. And I don't know, what do you write, C here, pretty much? Java, whatever.
C++.
Now, at the front end, the user does not have to see the temporal implications. Mm-hmm. At the back end, if you're using the inference engine to derive input-output behavior, I'm afraid that that's typically going to involve the regular expressions. C does not, you can't represent regular expressions in C. Mm-hmm. However, there was a whole list of, hey, you know, you've got your Google, you know, on the input side, you can have C or Java or whatever, but on the output side, you need something with the ability to represent regular expressions. Well, the grep is only it's just a utility, but these are languages. POSIX, which is what Google Code Search is based on. These are languages. So on the output side, you need something expressive enough, something that encompasses regular expressions. Mm-hmm. The input side, you can have Java, C, or whatever. But
are those languages Turing complete? Are those languages Turing complete, or?
No, okay. No, we're not doing Turing complete yet.
Okay.
Everything we're doing here is regular. That's an interesting research topic. How much of this, I mean, with finite state automata, mm-hmm. I mean, you can represent regular, I mean, in the hierarchy, that's at the bottom. Up at the top is Turing computable. Mm-hmm. I've given a little bit of thought on how one might extend this to the realm beyond regular, the context-free, context-sensitive, and Turing computable. That's strictly a research topic.
Okay. All right. Thanks.
Sure.
Okay, thanks again.
Thank you.